Well, we can start.
All right.
So good morning, everyone. Welcome to our IPARCOS-seminars. Today, it's my pleasure to introduce Dr. Nikki Zabel. She completed her PhD at Cardiff University, UK in 2020, working on the ALMA Fornax cluster survey. After that, she moved to Groningen, Netherlands, her home country, for a postdoc position until 2022. She is currently a postdoctoral researcher in Cape Town, where she primarily works with data from MeerKAT, FANGS, MUSE, MeerKAT Fornax survey, and connects it to the other cutting-edge instruments, particularly ALMA and integral field units. Her main research focus is the evolution of the galaxy in dense environments using multi-wavelength resolved studies of nearby clusters. Today, Nikki will present her talk, Nobody Touches the Dwarf, a resolved study of the multi-phase interstellar medium in low-mass galaxy in the Fornax cluster. Thank you very much, Nikki. The floor is yours.
Thank you, Erika, for the very nice introduction. And good morning, everybody from sunny Cape Town. Thank you so much for joining us today to listen to me, basically. Yeah, so I'm going to talk to you a little bit about a project that I published late last year about dwarf galaxies in the Fornax cluster. I've assumed that today we are quite a wide audience, both in terms of level and sort of expertise. So I'm just going to start from the very beginning and introduce galaxy clusters and all that stuff, and then we'll get into the projects. So when I think of galaxy clusters, this is what I always like to imagine. So a galaxy cluster is basically, we've got a very bright, very massive elliptical sitting in the center of the cluster, and then we have lots of satellite galaxies that are orbiting around this brightest cluster galaxy. And as you can see, those have all kinds of different sizes, different shapes, and they all fly on different orbits. And as a result, we get this very, very turbulent, very chaotic environment. And one of the reasons I always like to show this is that, of course, when we look with our telescopes, we get a very, very static snapshot usually of what's happening in the cluster, a very limited kind of time frame of what's happening. So it's kind of good to keep in mind how chaotic and turbulent things actually are. And besides the brightest cluster galaxy and the many galaxies flying around it, we also have the hot intra-cluster medium, which is basically a very, very hot plasma that is in between the galaxies in the cluster. So that is also important for the galaxy evolution that we study there. So this is reflected very well in the morphology density relation. If you do work on clusters, you will have seen this many times before. So what this basically shows is the fraction of a certain population of galaxies as a function of the number of galaxies per unit volume. And what you see very nicely here is that the spiral galaxies, which I've highlighted here with the blue line, they become less and less frequent as you go to denser and denser environments, whereas the elliptical galaxies that I've highlighted here in red, they get a lot more abundant if we go to denser environments, until in the very end, when we go to the densest environments in the universe, which is basically galaxy clusters, elliptical galaxies start to outnumber the spiral galaxies, and they are basically the majority as opposed to what we see in the field. So that kind of suggests that there is some things happening in galaxy clusters and in these dense environments that don't usually happen in the field, that kind of contribute to the more rapid quenching of the star formation in galaxies and to the sort of sped up evolution of galaxies that are in such environments. So again, if you have worked on clusters, you will have seen this one many times before. It's this very nice cartoon by Ari Chung. And she summarized very nicely the kind of most important processes that happen in galaxy clusters that are thought to contribute to this rapid evolution of galaxies in clusters. So some of them will have to do with the sheer number density of galaxies that we have there, and some have to do with the presence of the hot intracluster medium. So I'm going to highlight a few of them in the next couple of slides, kind of the most important ones. So first of all, we have what we call starvation or strangulation. So normally when a galaxy forms stars in the field, it's going to use up the atomic gas, the raw fuel for the star formation in the process. And it is believed that we need some sort of accretion of fresh supply of this gas for the star formation to keep going, because otherwise the galaxy would eventually run out of gas. So in the field, we've got the circumgalactic medium, we've got maybe free-floating gas or gas from interactions with other galaxies that can sort of supply fresh gas for the galaxy to carry on forming stars. But because in the cluster galaxies are surrounded by this very hot plasma, this gas is basically not available. So as it continues to form stars, it will just slowly run out of fuel, and eventually the star formation will stop and the galaxy will become red and dead or retired. So that is one result of the hot intercluster medium. Nothing too spectacular, it just slowly runs out of fuel, and this will run out of quenching. Then we've got ram pressure stripping. So that is one of the cluster mechanisms that has received a lot of attention lately. So a lot of papers have been on ram pressure stripping. And basically it is more or less just a more extreme version of starvation. So the galaxies within this hot plasma, of course, are not static. You remember from the little video that they actually fly through the cluster on orbits on quite high, with quite high velocities. And what we get if a galaxy moves through the densest part of this hot intercluster medium at high speeds, we can get that besides the galaxy just slowly running out of gas, we can get a much more active stripping of the intercluster medium of galaxies. So the hot plasma actively strips away the intercluster medium. We can get some bending on the disk, sometimes bending of the disk depending on the angle of the ram pressure and the angle with which the galaxy orbits the cluster. Because it affects the gas more than the stars, we can sometimes get a shift between where the gas is and where the stars are. And in the more extreme cases, as you can see in this image here, we can even get these really spectacular streams and tails of gas, which you have probably seen in jellyfish galaxies and the like. So this is a really active stripping of the interstellar medium. And of course, this eventually will lead to the quenching of star formation. Then last but not least, we've got galaxy-galaxy interactions. So of course, clusters are very busy when it comes to galaxies. So there will be many interactions between the satellite galaxies in the cluster. And whereas normally in the field, when two galaxies encounter each other, they tend to merge. So that is one more important evolution mechanism in the field. In clusters, again, the relative velocities of these galaxies are very high. So often when they encounter each other, it doesn't necessarily lead to a merger, but instead we get this very violent, very short flybys and interactions that can really mess up the stellar content and the interstellar medium of both galaxies and leave them very asymmetric. And this can eventually also lead to the quenching of star formation. So that is sort of highlighting the most important evolution mechanisms in clusters. So today I'm going to focus on one galaxy cluster in particular, which is the Fornax cluster. So Fornax is one of the two clusters that is closest to us together with Virgo. So it's at around 20 megaparsecs. It is visible only from the south, whereas Virgo is usually, it's at a very nice space where we can see it both from the north and the south quite well, which means that originally it was actually studied a little bit less than the Virgo cluster, but recently we've had a lot of new instruments and telescopes and things in the south. So the studies of Fornax have really been catching up. And it's actually a really different cluster from the Virgo cluster as well. So compared to Virgo, it is much smaller and denser. It's got a virial mass of around 7 times 10 to the 13 solar masses, where Virgo is estimated to be more between 10 to the 15, 10 to the 14. So it's a little bit smaller, less massive, really a poor cluster. But despite this, the galaxy number density in Fornax is actually much higher. Per unit volume, it's got about 2 to 3 times the number of galaxies that Virgo has. So it's actually quite a different environment. And we also expect different environmental mechanisms to play more of a role in Fornax compared to Virgo. It's also more regular, more dynamically evolved. It's just a little more evolved, more still in the assembly state, so to say. So it does have some substructure. It has an infalling group, but compared to Virgo, it is kind of like looking spherical, looking a little more evolved, whereas Virgo has a lot of substructure, a lot of subgroups, and it's a little bit more of a dynamical environment. So also in that sense, it's a little bit of a different place. And because of all those things, and primarily because it's more of a core cluster or a very large group, Fornax is actually thought to be a bit more of a representative environment in terms of where most galaxies in the nearby universe are, sort of the core cluster, large group kind of environment. So it's actually really interesting also to study both clusters side by side and see what differences we can find as well. So the project that I'm going to talk about today kind of originates from my PhD time. So my PhD was on the ALMA Fornax cluster survey, which was the first complete survey of all galaxies in the Fornax cluster in CO to probe the molecular gas with ALMA. So all galaxies that at the time had a detection in H1, that was a single dish detection with ATCA, or far infrared detection with Herschel, were targeted with ALMA, and other than that, there was no selection criteria. So that means that we, excuse me, targeted a variety of galaxy types, so not just the massive spirals or anything like that, but we also targeted some ellipticals, and as I'm going to talk about today, a few dwarf galaxies as well. So we targeted a CO1 to 0 line with ALMA to study for the first time in a resolved way the molecular gas in the Fornax cluster. So I'll just quickly show you what the molecular gas data of a typical galaxy in the Fornax cluster looks like, just for reference. So this is NGC 1387, which is one of the high-mass galaxies in Fornax, and these are the kind of data products that we get from the CO observations. So on the left here, we've got the moment zero map, which shows you the distribution of the molecular gas. The beam of the ALMA observations is here, and a scale bar is there. So you can also immediately see that molecular gas is quite compact. And this is just a very nice looking regular molecular gas disk. As you can see, yeah, just a typical disk shape, nothing interesting going on there. If we look at the moment one map here in the center, that shows you the velocity field of the molecular gas. And again, you can see this is almost basically a perfectly rotating gas disk. On the right, I'm showing the same moment zero map as here on the left, but now it's overplotted on an optical image from VST to basically show you where the molecular gas is and how it is distributed compared to the optical part of the galaxy. And here, this is really showing just the very center of the galaxy. This galaxy is very massive. It extends way beyond this image. So it just kind of highlights, again, how compact the molecular gas is and how centrally located. And this arrow here points in the projected direction towards the cluster center. So because the molecular gas is so centrally located and so compact, basically one of the questions we were trying to answer with this survey and with a few other ones that are ongoing at the time is whether molecular gas can also be directly affected by the cluster environment. So we know that atomic gas is distributed in a very large, very extended disk, and it's for a very long time that this has been used to trace the environmental processes that I mentioned earlier, because it is very easily stripped from galaxies. Molecular gas is much more compact, it's much more centrally located, so it was not immediately clear whether it can also be directly stripped from galaxies. So that was one of the main goals of this survey. So now I'd like to show another galaxy from this survey as well. So this is FCC 90, and I'm showing the very same maps that I was showing in the previous slide. So you can immediately see that this one does not look like a normal molecular gas disk. We can see a lot of structure here, different maxima, many things going on. And if we look at the velocity map, we can see that it is not really rotating. We can, with a little bit of imagination, maybe see some blue shifted side and some red shifted side, but really the motions of the gas is very irregular, very turbulent. And if we look at where the gas is distributed compared to the optical, we can see that the molecular gas forms this big tail that extends almost outside of the galaxy. And it is very much, yeah, very turbulent, very disturbed looking molecular gas. And this is what we found in a number of galaxies in the Fornax cluster. Of the 30 that we targeted, we detected CO in 15 of them. And in 8 of those galaxies, the molecular gas looked very asymmetric and very irregular. So this is just a few examples of that. You can see another one-sided tail here in the direction of the cluster center as well, and some other asymmetries of the gas in these galaxies. So this is kind of what sums up the main result of that initial work, the initial look at the molecular gas in Fornax. So this is showing the molecular gas fraction, so the amount of molecular gas normalized by the stellar mass of a galaxy as a function of the stellar mass in the galaxy. So all the markers that we see here are from the Fornax cluster, and I'm comparing them here to the relation, field relation from X-cold gas. So the dashed line here is a rolling median from the X-cold gas survey, which is extrapolated here to the lower mass side. These are 1, 2, and 3 sigma contours, and all the markers are from Fornax. So the triangles, the purple and the blue ones, we can ignore for now. I just want to focus on the red and the black ones. So those are the ALMA detections that we have. And there are kind of 2 things that really stand out from this figure. One is that all the data points from Fornax are systematically below the data from X-cold gas. So there's one exception here. This is a very massive spiral. But aside from that, all the galaxies in Fornax have suppressed molecular gas fractions compared to galaxies in the field. It's not always a lot. These are still around 1 sigma, but systematically, they are definitely shifted to lower molecular gas fractions. The other thing is that I'm making a difference here between high mass galaxies and low or disturbed galaxies, galaxies with disturbed molecular gas in red and galaxies with normal looking CO, like in the first example here in black. And I just gave it away a little bit, but what is immediately clear here is that all the galaxies with disturbed molecular gas are the low mass galaxies. So there's this kind of cutoff here around 3 × 10⁹ solar masses, where every galaxy that has a lower stellar mass and that has very disturbed looking molecular gas. And these triangles here are the ones that are particularly asymmetric, so that have a very one-sided tail, that have a very asymmetric molecular gas reservoir. So it's really the low mass galaxies that we actually didn't necessarily even expect to detect that turn out to have the most interesting, most disturbed looking molecular gas reservoirs. Yep, so those over here. So I wanted to have a closer look at those dwarfs because from marginally resolved CO observations, you can only tell so much. So I basically wanted to put together more of a multi-wavelength picture to really try and understand what is happening to those galaxies. So we've got molecular gas from the ALMA Fornax cluster survey, of course. In the meantime, we were very lucky that the MeerKAT Fornax survey was completed. It was actually, it's now since a couple of weeks, I think 100% complete. So we now have resolved very high sensitive H1 observations as opposed to the single dish observations we had previously. So instead of the, I think there was only 1 detection of a dwarf galaxy before, and now all of them have been detected with MeerKAT, so that is cool. And then we have H alpha to trace the ionized gas as well. So some of the dwarfs were already observed in the context of the Fornax 3D survey. So they targeted the 33 brightest galaxies in Fornax. So that includes FCC 90, the one that I showed you earlier. There was observations of another dwarf galaxy from a different program on the archive, and then we requested observations for 4 additional dwarf galaxies with MUSE. So we have a sample of now 6 of the dwarf galaxies that we detected in molecular gas. So I'm just gonna jump straight into kind of the multi-wavelength image because, yeah, kind of looking at what the different gas phases looks like is yeah, kind of one of the more interesting things. So yeah, I'll just talk you through what we are seeing here, and then I'll show you the other ones as well. So in the top left here, we just have the MUSE white light image to give you some idea of what the optical looks like. In the top right here, we have the moment 0 map of the atomic gas. So the color image here is the H1 moment map at the highest resolution because that matches best the other gas phases. But I'm also showing one contour of slightly lower resolution cube because, as you will see in some other examples, sometimes the highest resolution we resolve out some of the more interesting features that we see in the galaxy. So just to make sure we don't miss any of that, we also showing this contour here. This arrow again points into the direction of the cluster center. In the bottom left here, we have the molecular gas map, so the same one that I showed you earlier. Those contours here are the same contours that we see in the from the white light image here. So the bottom two panels are zoomed into this square because the molecular gas and ionized gas are so much more compact. We have to zoom in a little, so that is just for reference. And then in the bottom right, we have the ionized gas map. So you can see that all gas phases in this particular case are very disturbed. The ionized gas is pulled out in the same direction as the molecular gas, basically towards the same side, but it doesn't necessarily overlap 100%. So we're going to look into that later as well, because that also has implication for the star formation efficiency. The atomic gas is also pulled out kind of in the same direction. It is asymmetric. It is offset from the center. So yeah, all three gas phases are asymmetric and show disturbances as a result of the cluster environment. So in the top right here, we have a similar image, except that now I'm showing the velocity maps. So in the top left here, we have the stellar velocities. They're a Voronoi bin to the same signal to noise. This is a dwarf elliptical, as are all dwarfs actually in the sample. So it is supported by turbulence. We don't see any rotation in the stars here. And now if we look at the gas phases, so this is where it gets particularly weird and interesting to me. We can see that there's not really any rotation here in the atomic gas. Same is true for the molecular gas, but we can also see that there is a velocity offset between the two. So yeah, the molecular gas is a lot more blue shifted compared to what we see in the atomic gas. So they are not necessarily co-spatial with each other, but they're also not necessarily co-moving with each other, which is actually, yeah, not necessarily what we would expect. In the ionized gas, with a little bit of imagination, there is still a little bit of rotation that we can see in the center here, but the gas that is at larger radii, the stuff that is being disturbed by the cluster environment, that really shows a lot more random motion. So basically, this galaxy is a bit of a mess. Next one is FCC 207. So this one is the only one that looks a little bit different from the others. It is also the only one that is really relatively quite close to the cluster center, at least in projection. And so basically, we suspect that this one may have been in the cluster already for a little bit longer, because as you can see here, the all three gas phases are quite truncated, but they are not necessarily looking very disturbed or asymmetric. So we suspect that some of the gas has already been stripped, it is already gone, and now we just have a little bit of gas that is remaining at the center here. So in particular, if you look at the atomic gas, which is usually much more extended and much more, but also much more easily stripped, we can see it basically has the same radius as the other two phases. So really a lot of the atomic gas has been stripped away, and we're left with this very, very truncated little gas disk sitting at the very center. So again, we don't see any rotation in the stars. With a little bit of imagination, we see some rotation maybe in the atomic and molecular gas, but you can see from the velocity scales that it is really just barely resolved, so we cannot really say much about that. And the same in the ionized gas as well. Another one, FCC 261. So again, quite similar to the first example, there is asymmetries, there's an offset in the H1 compared to the stellar disk. We can also see that there's now a big tail of atomic gas sort of in the same direction as where the molecular gas is pulled to and the ionized gas is pulled to. No rotation in the stars. We do have some rotation now in the ionized gas and the molecular gas. But again, the sort of relative systemic velocities don't always seem to overlap with each other. FCC2A2 is the first one where we see some rotation in the stars, and we see some similar rotation in the atomic gas and the ionized gas, so that is nice. They're still not completely in the same place, but they are looking a little bit more like they agree with each other, like they're more or less doing the same thing. But again, now it's the molecular gas that looks completely different from the others. It seems to be at a different velocity, and yeah, it is not doing the same thing as the other two gas phases. We again have some asymmetry. The H1 is again offset from the center, the same for the ionized gas and the molecular gas. You can see that in this case, there's still quite a bit of star formation going on, though. We have all these H2 regions that we are picking up. We are only picking up the molecular gas on this side, so where most of the strongest H alpha is. So I suspect there's probably more molecular gas here that is just below our detection limit, but in any case, we can say that the molecular gas is quite asymmetric, and most of it is pulled towards the side of the galaxy. There's two more. These two are actually quite interesting. So this is a good example as to why we should also look at slightly lower resolution H1. So we can see that it's got a huge tail of H1 away from the galaxy. We've got another asymmetry here towards the south and to the other direction as well. Molecular gas is also asymmetric towards the south, and the ionized gas also has asymmetries towards both sides. So this one is really undergoing some stripping. And again, the velocities are, yeah, not similar at all to each other. All three gas phases are sort of at different velocities. We see no rotation, so this galaxy is also very messy. Now we've got the last one, FCC335. So this one is actually, so both these galaxies are very far away, close to the virial radius of the Fornax cluster, and they are relatively close to each other on the sky. So at the moment, they are roughly 70 kiloparsecs apart in projection. And this tail of FCC335 that we see in this direction here is directly opposite to the atomic gas tail that we see in FCC332. So they're probably a little too far apart to be interacting now, but there's also not a whole lot of other galaxies in the sky in that particular location. So we suspect that probably they have interacted with each other in the past and have sort of like done some pre-processing on each other on their way into the to the Fornax cluster. So we can see again that the H1 forms an asymmetry to this side and to a few other sides as well. And the molecular gas is being pulled towards the same side, and the ionized gas as well. So here it looks like we have some nice looking rotation in the star, so that's cool. And we can even see some nice rotation in the atomic gas and the ionized gas as well. However, the only problem now is that the axis of rotation for both these gas phases seem to be completely perpendicular to the axis of rotation for the stars. So that is also something I haven't really seen before. So it could be that maybe that's a result of the possible interaction that I was mentioning earlier. Maybe it is possible that something like ramp pressure stripping, depending on the angle, could sort of like change the rotation axis of the gas or something like that, but it looks quite unusual, and like a lot is happening to this galaxy as it's falling into the Fornax cluster. Again, in the molecular gas, at least now the systemic velocity kind of makes a little bit like it's a little bit more similar to the other two gas phases, but it's not following the same rotation at all. It's kind of doing its own thing. So again, this galaxy is also very messy. So I basically tried and put this complete like multi-wavelength picture together to try and understand better what is happening to these dwarfs, but it's kind of left me with more questions than I started with. Okay, so a few additional things that we can do with the MUSE data is to look at the BPT diagrams to see what is the origin of the ionization, or the reason that this gas is ionized. So I kind of assumed that all the ionization would just be due to star formation, because these are small dwarf galaxies. We don't expect them to have an AGN or anything like that necessarily, but I thought, okay, just to double check, I will have a look at the BPT diagrams and see what the source of ionization is classified as. And indeed, like most of the galaxies, it is just pure star formation as we expected. But the last two galaxies that I showed, FCC 332, FCC 335, the source of ionization is actually not necessarily star formation. A lot of it is composite, so sort of in the transition region where some of it is because of star formation and some of it other sources of ionization, which could be AGN or could also be something else like shocks or old stars. And in this case as well, some of it is classified as composite or transition area, but a lot of it is also classified as definitely not star forming, but something else like AGN or shocks. So there's no evidence for AGN in any of these galaxies. They're all dwarf galaxies. As far as I'm aware, none of them have anything like that. So we suspect that instead this gas is ionized because of shocks. And that could also, again, be the result of an interaction between both galaxies where maybe the gas got shocked because of that interaction, or maybe it's being shocked as they fall into the cluster, something like that. So yeah, that's also an indication of these galaxies being processed by cluster effects. So to look a little bit more into sort of the velocity offset between the molecular and atomic gas, because it is really kind of unexpected that we find the gas at different velocities. So in order to look at that into a little bit more detail, I looked into the position velocity diagrams of a few of these galaxies. So I tried to sort of make them along the major axis of the atomic gas as far as that's defined. It's not always very well defined in these cases. So we see the atomic gas in blue, and I overplotted the molecular gas in red. And of course, the scales and the resolutions are quite different, so it is not always easy to see. But in these two examples, we can again see very clearly that the molecular gas is at a very different velocity from the atomic gas. They're not at all in the same space in the position velocity diagrams. So yeah, that is quite interesting. So to put things into a little bit more context and a little bit more perspective, I also looked at some scaling relations. So this is just the star formation main sequence. We can ignore most of the colored markers here, but in black I'm showing where galaxies from the zeroid main. Now I forget what the exact acronym is, but from a huge field sample, basically where they are on the star formation main sequence. The pink line here is the star formation main sequence from the X-cold gas survey. And our dwarf galaxies are highlighted here in red. So we can see that a few of them are still quite close to the star formation main sequence. They are a little bit less star forming, than just a little bit outside of 1 sigma, basically, which is the dashed lines here, but they are still reasonably star forming. And there's a few of them, the other half of the sample, that are quite far below the main sequence, so they are not really forming stars anymore. Another scaling relation to that I think is interesting to look at is to look at, well, it's not necessarily a scaling relation, but to look into their gas deficiencies. So the gas deficiency is basically defined as how much gas do we observe in a galaxy compared to how much gas do we expect to see in a galaxy based on what sort of an average galaxy in the field looks like. So in this case, I'm defining the expected gas mass based on the typical gas mass that we see in a galaxy, in a spiral galaxy in the field with the same stellar mass. So the deficiency is basically how much less gas we observe compared to how much gas we expect. So I'm showing here the molecular gas deficiencies as a function of the atomic gas deficiencies for our dwarfs here that are the stars, and for other galaxies both in the Fornax and Virgo cluster. So you can see that there's a little bit of a general trend where a few galaxies are kind of rich to normal in H1 and H2, but most cluster galaxies are in this quadrant here, where they are both poor in molecular gas and atomic gas. And our dwarfs kind of follow that trend. So there's a few that have relatively normal molecular gas, but most of them are up here. And what we can also see is that most galaxies are much more deficient in atomic gas compared to molecular gas. So they are a little bit deficient in both, but the deficiency in atomic gas is much stronger than the deficiency in molecular gas. So for example, these ones up here, they have about 100 times less atomic gas than a similar galaxy would have in the field, but their molecular gas efficiency is only 0.5. So this again kind of highlights what we also saw in the resolved picture of FCC 207, which is that most of the atomic gas will be stripped before most of the molecular gas is stripped, which makes sense because it is a lot more extended. Molecular gas is much more compact and harder to strip. But yeah, we could still see earlier that both of them are being affected at the same time. Both of them are being removed and stripped from galaxies at the same time. But still, most of the atomic gas is going to be gone before serious amounts of molecular gas are going to be stripped. So that's kind of what we see here. So both of those things, especially because some of them are still quite a bit forming quite a bit of stars, kind of begs the question, okay, this gas is very turbulent, it's very disturbed. How efficient is it still at forming stars? Because we can see in a few cases there is still active star formation. So what is sort of the effect on the star formation efficiency? So from MUSE, we've got the H-alpha measurements that can give us a star formation rate surface density, and from our ALMA observations, we get the CO, and we can derive the molecular gas surface density. And if you plot those two things against each other, you get the Kennicutt-Schmidt relation. So that basically tells us how efficient the star formation is in these regions within the galaxies. So here's what that looks like for the Fornax cluster, and in particular for these dwarfs in the Fornax cluster. So the gray points are resolution elements of every other galaxy in Fornax that is not one of the dwarfs that we study here. So that is, that is kind of where Fornax galaxies are on the resolved Kennicutt-Schmidt relation. And the colored kernel density estimate plots here, each of them corresponds to a dwarf galaxy. Then there's a few relations from the fields that we are comparing with. So the pink one here is the original Kennicutt-Schmidt relation. The light blue one is the relation from Beguil et al. 2008. Which is kind of more similar to what we're doing here, because the original Kennicutt-Schmidt relation is unresolved observations of spiral galaxies and starburst galaxies, whereas this one over here is also a resolved study, and it also includes a more diverse pool of galaxies. So that one is probably the most comparable field sample to what we are doing here. The other three, so the green, yellow, and purple, are all three from the Virgo cluster. I'm not going to distinguish between the three here, but this is, kind of the slope that we found in the Virgo cluster as well. So you can see that there's quite a bit of variety both between the different dwarf galaxies, but also within them. So there's a few that are kind of agreeing with the field relation. So they are kind of normal in terms of how efficient their star formation still is, or maybe even a little bit more efficient than what we see sometimes in the field. But most dwarf galaxies are below the typical field relation. So they have more inefficient star formation, which is maybe not unexpected. So you can draw lines here of constant depletion time. So if you divide both axes by each other, you can get a measure of the depletion time. So basically, if a galaxy continues to form stars at the same rate as it is doing now, how long will it take for the galaxy to completely run out of molecular gas? So you can see a bit from the field samples here that in your average spiral galaxy in the field, usually this takes about 1 to 2 gigayears, but some of our dwarfs are more scattered around the 10 gigayears. So it will take a long time for the galaxy to run out of gas because it is not using it efficiently to form stars. So because we have resolved observations, you can also map this for each galaxy. So basically just dividing the star formation rate surface density map and the molecular gas surface density map, you can get a measure for the depletion time in each pixel. And you can also study the resolved Kennigan-Schmidt relation for each dwarf in a little bit more detail. So this is again FCC 90 that I've been using as an example. Again, this is the Kennigan-Schmidt relation and the relation from Beguil. And you can see that there is quite a bit of difference within this galaxy as well. So most of it overlaps with the Kennigan-Schmidt relation. So the gas is still kind of forming stars at a normal efficiency, but there is also some points here where the star formation is quite efficient, and also some regions where the star formation is much less efficient. And if we look at the map and see what regions that corresponds to, we can see what I think is very interesting in this case is that all the gas that is kind of central to the galaxy, the molecular gas that is in the core of the galaxy, is forming stars very, very efficiently. So the depletion times are scattered around sort of 0.1 gigayears. So the star formation there is very efficient. Whereas the gas that is being stripped from the galaxy, the gas that is very close to the outskirts of the galaxy, has very, very long depletion times. So that is a gas that corresponds to these points over here, where the depletion times are closer to 10 gigayears. So whatever is happening to this galaxy is undergoing some interaction. It's maybe undergoing some ram pressure stripping. It is causing a little bit of a almost star burst in the core of the galaxy. So the star formation is having, just being stimulated there, whereas the gas that is being pulled out and that is being stripped is becoming very inefficient at forming stars. So this is FCC 261, just to show a little bit of a different example. So this one has very, very slow, very inefficient star formation. The vast majority of regions is here scattered around the 10 gigayears. And you can see that in this case, when we look at the core of the galaxy, this is where the star formation is also very inefficient, so sort of 20 gigayears and above. So again, there is differences within and between all galaxies here. So that's all I had to say today. Basically, the summary is dwarfs are very messy. We can see that the morphologies in all gas phases look disturbed. They're usually kind of pulled out in the same direction, but they are not always co-spatial with each other, which is also why we see these differences in star formation efficiency. If we look at the velocities, it gets even messier. In not many cases, we can see clear rotation in any of the gas phases, and there is differences in sort of the systemic velocities between the gas phases and also between the stars and the different gas phases as well. So the things that we do see, I didn't really touch upon this, but the morphological disturbances and especially the disturbances in the velocity field that we see are not consistent with just only ram pressure stripping. It looks much too messy for that. So there's probably other stuff going on as well, like interactions between the galaxies, maybe even before they properly enter the cluster. We saw from the gas deficiencies and from the morphology of FCC 207 that the majority of atomic gas is going to be removed before most of the molecular gas is removed, which is now being seen in various studies as well. And as a result of all these disturbances, most dwarf galaxies are very inefficient at forming stars, although there are some exceptions where the star formation actually seems to get a little bit of a boost, especially in the central regions of the galaxy. So what is happening to the dwarfs? So probably, I also didn't really spend much time talking about this, but most of them, except FCC 207, are really scattered around the virial radius of the cluster. So probably they are on their first infall and they're busy transitioning from star-forming galaxies to quiescent galaxies. And they're experiencing a lot of environmental processes as they are falling into the cluster. And it could be that some of them are interacting or have been undergoing some pre-processing before entering the cluster. For example, FCC 332 and 335 that are kind of entering the cluster together, and they may have interacted before they started falling in. So that's all from my side today. Thank you very much, and I'm happy to take any questions. I'll leave the summary up.
Thank you very much, Nikki. Very interesting talk. So we have time for questions. You can unmute your microphone if you wish and ask you. Patricia, yes, go ahead.
Hi, thank you very much for the talk. Very interesting indeed. I was wondering that if also like the depletion between H1, H2, or the depletion with respect of to the galaxies in the field of cold gas that you saw is also related with the position of the cluster. I mean, if it's compatible with this vision that the galaxies that are in the outskirts are also the ones that have less depletion in H1.
Yeah, so basically all of them are at the outskirts. So it's only 207 that in projection at least is close to the cluster core. And in that case, everything looks like it's a little bit more settled. So yeah, it looks like only the ones that are sort of actively falling in have that weird discrepancy. And 207 that is probably has been there for a little bit longer. Everything seems just to be a little bit more settled. It seems to be, yeah, more consistent with each other, just like a truncated little gas disk, yeah.
And do you have, I mean, the signal to noise in MUSE is enough to do an extrapolation analysis? Have you looked at the stellar ages or?
Yeah, so that is something we are working on at the moment. So far, I've only compared the gas phases with each other, but there are some collaborators in Groningen and in Ireland as well that are more expert in looking at the star formation histories and looking at the ages and things like that. So in most cases, the signal to noise is actually quite good, so it is possible to do that. So there's a student in Groningen that is currently working on that, and yeah, they're in Northern Ireland. They're looking into that as well. So that is ongoing work. Yeah.
Okay, excellent. Well, just the last one, if I'm allowed. You mentioned that the star formation rate, when you saw the main sequence for the first time, it was written there that the star formation rate was calculated with WISE. So with the
Yes.
Okay, so I was wondering if you have compared that with the H alpha measurements, just because.
Yeah, I'm thinking now that may have been an old slide because now obviously we've got the star formation from H alpha as well. So I think the ones that I actually previously we didn't have that, so we used WISE, but I think what I showed you was actually
H alpha, okay.
Information from H alpha. Yeah.
Okay.
So in that case, I have assumed that all the H alpha is actually star forming, which may have been, a bit of a stretch for those two galaxies where we saw that the H alpha is not necessarily as a result of star formation. So in those cases, it's kind of upper limits in that sense. But yeah, we do have star formation from the H alpha now. At least for the dwarfs, not for all of them.
Yeah, okay. Did you just out of curiosity, did you compare both? You don't remember? Okay,
maybe, but I don't remember. I don't remember how well they agree.
Okay. Well, thank you very much.
Thank you.
Any other questions? Well, I found very intriguing the different morphology in kinematics that you found in this kind of galaxy. And I was wondering if you also have the possibility to make a similar comparison with other kind of galaxy in the cluster, like spirals or ellipticals, and if you found a similar relation between the morphology and the kinematics of the different phases.
Yeah, I haven't actually looked into that in a lot of detail. Yeah, we can do it for a lot of galaxies, especially spirals, because there is MUSE for all the most massive galaxies and all of that. But because they look a lot more normal, like they probably agree a lot better, but I haven't gone and like made those figures for all of them. So you should probably do that for a few and see what it's like, yeah.
No, but it's true that the one that is more intriguing, which is the one that the H1 and the ionized gas, these are rotated in different angles, no? Or
perpendicularly.
That looked that was the galaxy that looked more normal, like more yeah.
Yeah, at first glance it looked more normal, and then I was like, oh, hang on. Yeah.
It'll be interesting to see that.
For what concerns the extension of the molecular size, could be due to a sensitivity effect, or I mean, do you expect to to find larger extension of the molecular size, or?
Not necessarily, I don't think. I don't remember from the top of my head how deep is the survey, but we did everything sort of at the same sensitivity, where we do expect to pick most of it up. Because they are dwarfs, of course, there is also a bit of a metallicity issue. So it could be that we're not picking all of it up in every case. For example, in the one that I showed that has a lot of star formation, there should be some molecular gas associated with those regions where we can clearly see H alpha, but we're not picking it up. So I think maybe we are missing some of it, but I think in most cases we should be picking most of it up. Yeah.
Okay.
Yeah, I wanted to do, because of course because of metallicity effects, we expect there to be relatively a lot of CO dark gas in dwarf galaxies. There have been a lot of studies on that. Also suggesting that maybe C+ is the better way to pick up molecular gas in dwarf galaxies. So it actually meant to go back and put in a Sophia proposal to see if maybe in that way we can find more molecular gas in dwarfs, but then it got defunded and that didn't happen, and now we cannot access that way. Yeah.
Pity.
But I think in most cases we should be picking most of it up.
Okay.
Maybe, comparing with WISE, maybe you can get an idea of the where you are missing some molecular gas.
Yeah, that's a good one.
And in the Virgo cluster, do you know if the morphology and the kinematics of the different phases also is so strange as in the Fornax class?
There's not so many observations of dwarfs in Virgo. I'm actually pushing to try and get a bit more of them, because all the Virgo studies that I know just only focus on spiral galaxies, on massive spiral galaxies. So there's a few that were observed at the kind of lower mass end, but that's only a handful. And so far, let me think now. Yeah, there is an ongoing MUSE program, but I haven't seen the data of that yet. In terms of molecular gas, I think there is some that look a little weird, but I haven't put them side by side. And I'm thinking now about atomic gas. Yeah, there is some VLA of most of them, and there's also an ongoing Virgo MeerKAT survey. So I'm hoping I'm hoping that soon we can do a similar sort of study for that one, but the data is sort of like incoming from all angles. So yeah, and I'm trying also for some more CO follow-up of the lower mass ones, because that doesn't really exist. So would be cool to do the same.
Thank you.
Thank you.
So, any other questions? Well, if not, I think we can stop here. Let's thank Nikki again.
Thank you.
And thank you very much
Thank you all for coming.
Thank you.
Everyone,
Say hi to
for joining
Ilani
us.
for me. Nikki?
Hmm?
Can you say hi to Ilani from me?
Oh yeah, of course I will. Cheers.
Bye.
Okay, so thanks again, Nikki.
Thank you.
See you.
Bye.
Thank you. Bye.
Thanks.
Bye.
Bye.
Bye.